Yeah, I taught statistics for 20 years in a business school, and then I came and joined AIP Statistical Research Center. So I want to thank y'all for giving me a chance to get a little bit back to the teaching mode. I think it'll be fun. I hope it's fun for you. And why isn't my slide? There we go. So I know y'all know what SPS is, and maybe you know that SPS is part of AIP. My division is the Statistical Research Center, and we gather a lot of data on statistics. Yeah, I think that's pretty explanatory. These are some of the things. Now, this physics trends flyer, I hope that you saw on a faculty member's door, because we sent those out last fall. We produced the rosters of the physics departments. This page might be of great interest to you. It's who's hiring physics bachelors. So this is a state-by-state listing of employers who hire people with physics bachelor's degrees, who have hired them in the last 2 or 3 years. We also include their common job titles, the careers toolbox. If you've seen the careers toolbox, a lot of that data came from us. If you haven't seen it, you should look for it. It's the SPS careers toolbox. You can even go sign up for our e-updates and get free data alerts on what's happening. And then I'm going to draw your attention to this physics trend flyer. It's the one that went out in the mail. So I don't know if your school got it, but it'll be there when you get back to school. One of the 3 that went out. And this data is from a national survey of placement officers, and it's who made job offers and how much they were offering by major. So physics does very well there. We've been collecting data since 1961. As I said, we are the sole source for what data on students with the physics degree do. So we get that by surveying you 1 year after you earn a degree in physics. So if you get an email from Pat Mulvey, please respond to it, because you're helping produce data. One thing we know is about 50% of those who earn a bachelor's degree in physics go on to grad school. About 2/3 of those go to grad school in physics or astronomy, but that's 1/3 that go in something other than physics or astronomy. All right, now I've got our first poll coming up here. So, number of women earning bachelor's degrees in physics has done what since 1976? Has it declined? Has it remained constant? Increased a little bit? Doubled? Tripled? Quadrupled? Quintupled? I know 1976 is a long time ago. Why 1976? It was our bicentennial. Okay. It's the year the Smithsonian Air and Space opened, which was a really exciting thing. And is anyone voting in our poll?
Yes, we have 4 of 9 people. Oh, 5 of 9 people have voted.
And what are they voting?
Right now we have 4 people voted for doubled, 2 for increased slightly, and 1 for tripled.
Well, here comes the response.
Okay.
It has quadrupled since 1976. That might be a little counterintuitive, because maybe you don't see a lot of women in your physics classes. And it's true, women comprise about 20% of physics bachelor's degree recipients. But notice the total number of degree recipients has gone up really in the last 20 years. It's shot up dramatically. The curve here goes down a little bit. If you want to look at the proportion of women, bachelor's degrees is sort of leveled out. PhDs is, well, it's around 20%. So we're hoping to do better, and you might be wondering, or maybe you're not wondering, but I'm going to tell you anyway. How does this compare with other fields? Well, this is a representation of women among students earning degrees in biological sciences, chemistry, math, astronomy, computer science, And we're right down, physics is right down here with engineering. There have been a lot of programs to try to increase the representation of women. We also need to increase opportunities for women. So that's been the advertisement for our data. And now I'm going to move on to something you may or may not have seen. I've got people in a room here. And how many people do I need to have in a room? And I hope it's, what is it, 50? Is 50 the magic number now with our coronavirus? How many would we need to have at least a 50% probability that 2 had the same birthday? At least a 75% probability at least 2 had the same birthday? At least a 99% probability. Well, 99.9. And how many would we have to have in the room to be sure? Well, we'd have to have 366, because there's 366 days in the year. I'm going to count leap year. I have a friend who was born on February 29th. She just turned 4. No, she just turned 5, and she's into college as a 5-year-old. So we're quite impressed. I see no guesses coming up in chat. So I don't know.
Yeah, anybody got a guess?
All right. Well, this is what's known as the birthday problem. So if there are just 2 people in the room, it's pretty simple. The first one's going to have some birthday, and I am assuming the 366 days in the year. And it's easier to think about the probability they don't have the same birthday than the probability they do, because probability they do, you'd get into all sorts of combinations and permutations because you got 366 different days it might be. So the first person's birthday is some date. The probability it's that date is 366 out of 366. The second person's birthday has a 365 out of 366 probability of being on some different day. So we assume birthdays are independent events. So the probability the birthdays are not shared is simply the product of the 2 probabilities, pretty high, which then means the probability they are shared is pretty low. So that's with 2 people in the room. If I add a third person, I just add the next term. And that's pretty low. And I can carry this out all the way to 366. We're up to K people in the room, and it's going to look like this, but there's a simplification. I can gather up the terms. I get 1 over 366 to the K, where K is the number of people in the room, times 366 down to 366 minus K. So those are the calculations. And we get a graph that looks like this. This is the probability the birthdays are shared. Remember, I said 50%, so it's right along in here. In fact, I'm going to get rid of the not shared part. So here's the shared. The 50% is right here. The 75% is right here. And the 99.9% is right here. In fact, it would take 23, 32, or 70. So I guess these days we can't get 70 people in a room, but it can make an interesting, I don't want to use the word bet, it can make an interesting challenge with your students. I used to do this with my students. I'd tell them, I had a class of about 40, and I'd say, okay, we're going to have a pop quiz if 2 people in the room have the same birthday. They were always relieved because they thought, great, but they didn't realize it was going to be a pretty high chance that we were going to have a pop quiz. I want to move on to another statistics problem that you may or may not have seen. It's the let's make a deal problem. I'm going to show you 3 doors. Behind one door is a fabulous prize. If you've seen the movie A Christmas Story, you might even think of it as a major prize. I'm going to let you select any door, A, B, or C. And once you've selected your door, I'm going to show you what's behind one of the other doors. And then I'm going to give you an opportunity to switch. So, visual representation, here's my doors, A, B, and C. And remember, I have a fabulous prize behind one of these doors. The question becomes, should you switch? So I want y'all voting on this. And what are our answers coming in this time, Michaela?
Everybody so far has said 2/3 of the time.
Oh, wow, y'all know this problem.
And then somebody asked, is the assumption that the reward is not revealed?
That's a very good question. Yeah, I've prepared a simulation, which I've got my laser pointer thing going and I can't turn it off here. And yes, I will show you the dud. So if the prize is behind A and I pick A, he can show me B or C. I switch to the other one and I don't win. But here on row 5, if the prize is behind A and I pick C, he has to show me, sorry, I pick B, he has to show me C. I switch to A and I win. And as you expected, of course, this is a simulation that I program in Excel, so it's going to change slightly, but if I did it an infinite number of times, you would switch and win 2/3 of the time. And we'd be dancing happily. Of course, the sad truth is you're really only going to play it once, and that one time you play it might be one of the 1/3. And then we're all just sad for you. But what I really did for many years was applied statistics. And I want to just give you a little introduction to applied statistics. And applied statistics actually started in ag schools because farmers wanted to increase their yield per acre. So of course, when you're planting your crop, you don't know what the weather is going to be. You don't know about the weeds and diseases. There are a lot of things you don't know. So what can you do to maximize your yield? Well, you rely on the researchers who've run designed experiments. They plant a crop and they see what happens, and they do that systematically. And when they're through, they partition the variation in the results into variation due to things I can control, like whether or not I water it, whether or not I use an organic pesticide, whether or not I add fertilizer, and the variation due to things I can't control. The weather is the big one there. In this field, we're not going to get into whether or not what's happening with the prices of the goods I'm trying to sell. And there's going to be several replications for each of the different sets of conditions you can control. And this, wow, especially when I don't have any non-visual clues. So for condition A, which might be a particular seed density with no fertilizer, no organic pesticide, I'll plant 4 fields. For condition B, maybe I vary the seed density and that's all, and I plant 4 more fields. Condition C, maybe I add some fertilizer with a set seed density. Condition D, I change something. But the important thing here is I've replicated the conditions 4 times each. And I have to replicate the conditions so I can start partitioning out the variation. So when I get through, there's the variation due to things I can control and the variation due to things I can't control. I've kept it all pretty simple here, making it all add up to 100. Which one looks the best? Or let me ask it a different way. Is our goal to reduce the variation due to things I can control or due to things I cannot control?
Or 50-50.
Oh, 50-50.
Oh, now it's 3-2 to things you can control.
So you think variation of things we can control. Well, it's counterintuitive. You want to look for the smallest variation in what you can't control, because you're trying to minimize that variation. So one of those conditions, and I'm going to go back very quickly, this condition, condition D, had the smallest variation to things I can't control. So I'm going to take condition D, and then given that I'm using condition D, maximize the output given the things I can control in condition D. Is the variation metric indicating a factor of yield increase? No, it's just, it's variation in yield due to what I can or cannot control. Maybe that is what you're asking me. But I've got a real life example that might help. So I taught in Louisiana for a while, and we were near a lumber mill, and one of my students worked for the lumber mill. They made 2x4s. He was the plant manager. And how do you make a 2x4? You get a tree, you cut it into 2x4s. You cut it slightly bigger because the tree is green and wet. And then you're going to dry it. And you're drying it in a very large room, like a gym. It's not insulated from the weather. So who knows what the outside weather is going to be, if it's going to be hot and humid, cold and dry, don't know. There's 3 basic things I can control. There's a setting called the wet bulb setting, a setting called the dry bulb setting, and that's having to do with how quickly you change the humidity. Both of those working together do that somehow, I don't know. And then the length of time you let it dry. And you got a lot of lumber in there, so you want to get it right because you don't want to waste all that lumber. So you control your wet bulb, your dry bulb, your length of time. You hope your drying goes right. They let us run a design experiment on this. They basically gave us control of their kiln for 6 runs where we could change these settings systematically. And once we were done, we picked the set that had the smallest variation due to things we couldn't control. And then we maximized the output. And it actually increased their grade A lumber yield by 50%, which they were very, very happy about. Because the grade A lumber is the one you can sell for the most. If you get it too dry, you can't sell it at all, I think. And if you get it wet, you can't sell it for as much. So that's a concrete example. Now, where I'm coming from, we have statistics because we don't know the truth. And it's a systematic way to estimate the truth. And in some sense, I can give you the probability I got it wrong. Statisticians are rolling over in their graves for me using that terminology, because that's not really what it is, but sort of what it is. Another question, can I prove something with statistics?
Okay.
What have we got?
We've got half and half some of the time and no.
Okay. I think I know why we got some of the people saying some of the time, but we'll talk about that. The answer is no. How do we do it? We do it with hypothesis testing. We assume something, we call it the null hypothesis. We have an alternate hypothesis that's the opposite of the null. I test it. I either reject or fail to reject my assumption. Now, the question is, if I reject the assumption, have I proven that the opposite is true? And the answer is no. Why not? Well, because there are two errors I might make that are important enough that statisticians who are quite creative people have named them. They're so creative, they named them a type 1 error and a type 2 error. They tried. But one error I might make is I might reject an assumption when it's true. So my null hypothesis might be true, but I reject it in favor of the alternative. Or I might fail to reject an assumption when it's false. So I never get to the truth, which was in the alternative, and I keep thinking the wrong thing. Type 2 error. Now, in statistics, I can control the magnitude of my type 1 and type 2 errors. Magnitude is not the right word for a physicist. I can control the size of my type 1 and type 2 errors by different things that I do in the experiment. And it's not that type 1 error plus type 2 error equals 1. That's not true. But you have to decide which one you think is worse and decide whether you want to control more for type 1 error or type 2 error. And which one's worse? It depends. Let's say I'm a pharmaceutical company and I'm making some drugs and I want to see if they work. Maybe I'm working on creating a drug to address coronavirus, COVID-19. Now I'm going to assume the drug doesn't work, and my alternative will be that it does. So one error would be rejecting the truth that the drug doesn't work, and I'm going to produce and market a drug that doesn't work. The other error would be failing to reject the false assumption that the drug doesn't work, in which case I don't produce and market a drug that would work. In this case, which do you think is the worst error? And there's no right or wrong answer here. You have to decide. Personally, I think the first one is worse than the second one. I really don't want to produce and market a drug that doesn't work. But if you do that, you run the risk of not producing and marketing a drug that would work. So, I don't know if y'all know Post-it notes. A 3M employee sang in the church choir and got tired of watching all the little old ladies would they would mark the hymns for that week's services. They'd tear little pieces of paper and stick them in the hymnal. And the 3M engineer got tired of looking at all the little pieces of paper on the ground in the choir loft. And he remembered this adhesive that they had made that didn't really work very well. And he thought, well, this is perfect for that. So he took it, and the choir ladies loved it because they could move it from page to page. He tried to get 3M to market it. They said, why would anyone ever want to buy an adhesive that doesn't work? So they originally made a type 2 error there. Another look. In our legal system, we assume the defendant is innocent. The alternative is they're guilty. So we might make two errors. We might convict an innocent defendant, or we might let a guilty defendant go free. Which is worse? Who knows? In the US, we assume they're innocent. In the US, we have decided that convicting an innocent defendant is the worst mistake. In some other countries, they assume the defendant is guilty, which then by default, they're assuming letting a guilty defendant go free is the worst mistake. It's just a choice societies have made. You may be wondering, will I ever use this in statistics beyond StatMech? Absolutely. Experimental physicists rely on applied statistics all the time to help them test their theories. Can't really prove a theory. I might fail to disprove it, and I'm going to claim failing to disprove it is a weak result. The other thing that might happen is I might disprove a theory, which I'm going to claim is a much stronger result. Any thoughts on why I would claim that disproving a theory is a stronger result? Remember, disproving a theory means I rejected the null hypothesis, and there is that type 2 error where I might have, that's type 1 error where I might have rejected a true null. True null says the scientific method. Yeah, pretty much anytime you can come up with a counterexample to something, you've done a good job. And people are going to go look elsewhere.
We've got another comment. Failing to disprove doesn't actually tell you very much.
Yeah, I see that's from Jeff Nunn. You're right, it doesn't actually tell you very much, but sometimes it's the best you can do. You don't have the capability to do anything else. In physics, this is from Physics Today, November 2019. The radius of the proton, and let me highlight. Somebody measured a proton radius is 0.84 femtometers, which I'm imagining is pretty small. And it was 5 standard deviations smaller than the originally accepted value of 0.88 femtometers. And why is that 5 standard deviations so important? It's because if you do things right, if you have enough data, your estimate's going to follow a normal distribution, which means 99.9% of the time you should be within 3 standard deviations. So it's very unlikely you'd be 5 standard deviations away if that original measure was correct. I know there's a faculty member at GW, Evie Downey, who is working on this exact problem, trying to come up with some understanding. They're using 2 different ways to measure it. I'm not a physicist. I should probably stop trying to say more than that. But one of the questions is the way it's being measured changing the radius as part of the measurement, I think. And I just want to say thank you. I hope you recognize the picture. It's from Jack Nicholson and A Few Good Men. And what is he shouting? I'm waiting for someone to type in chat. Yes. He is shouting, "You can't handle the truth."
Yeah.
Any questions, comments, other remarks? Please do stop by aip.org/statistics and check out our data. There's a lot of stuff there that you might find useful, particularly the Who's Hiring Physics Bachelors. We also have a Who's Hiring Physics PhDs if you hope to go on. Hint, it's not all academics. Those who go into private sector make a lot more money than those who go into academics. Of course, well, everybody has different pressures. In fact, we just had a report we produced from our PhD plus 10 on people being happy where they are. How did I get to where I am? Excellent question. I got a BA in English and I was never going to go back to school. I got that BA in English because my first semester I was a math major, second semester computer science, third semester I didn't like being math because I made a C in calculus. I later found out if you made a C in calculus from that professor, you should have majored in math. Nobody told me that. Computer science, I was in the day where you had to turn in the punch cards and wait overnight to see if they ran. I didn't like that. Then I went to chemistry. The afternoon labs interfered with my intramurals. So I went to English. I could still get out in 4 years. I was never going back to school. Well, went back and got an MBA. Met a guy from Louisiana, married him, started teaching. Then decided to go back and get my PhDs in management science, which is, in addition to statistics, includes optimization methods, some AI methods. So then I was teaching in a business school. My husband got the job as the SPS director. We moved up here and I taught at GW. We moved up to the DC area. I realize y'all may not all be here. And I taught at George Washington University in the School of Business. Then an opening came, a spot came open in the SRC, and Gary worked at AIP and knew the SRC was a great place to work. So I applied and I got it and I've loved it. I have wonderful colleagues who really, if you have a question, just email us and we'll try to get you an answer. We'll let you know if we can't. And in an interesting twist, my husband now teaches at GW. So we've kind of traded places. He's teaching in the physics department there and is in fact the SPS advisor. Was my AI work in neural networks? How did you know? My dissertation was time series forecasting in radial basis function neural networks. That's a long time ago in another world, but it's amazing all the things that we can do with AI, and it's amazing all the things we don't know about what we're doing with AI. The problem, we just don't know a lot about the statistics in feed forward neural networks because there's so much that's hidden in them.
If there's any other questions, if you want to put them in the chat now.
And I'm curious why you ask if it was neural networks. Are you interested in neural networks? Have I worked on any statistical analysis of patterns within convolutional neural networks? No, I have not. That sounds really complicated. And I have to confess, I go back and look at my dissertation now and I look at where I'm deriving all these formulas, double integrals, and I think, wow, at one point I knew what I was doing. Now you don't use it, you lose it. It's true. Working at a startup leading neural network development. Well, good luck. And I mean, there's my email, S. White. If you want to email me any other questions, I can tell you what I know, which If you're interested in convolutional neural networks, I'm not going to be much help at all. But some of these seminal papers in neural networks were in physics journals, by the way. Or, sorry, they were by physicists at Los Alamos.
Okay, I guess, any input you might have.
On neural networks, if it's on neural networks, just send me an email, swhite@aip.org. Good, you will email me. Good. Anyone else is also free to email me. But y'all have been a wonderful audience. I think maybe I'm a guinea pig, Michaela, is that correct?
Yeah, so you're the first of our series of talks, and I think it went pretty well.
We want to keep y'all engaged. We know that suddenly you are no longer on campus with all your friends and colleagues. You are at home, probably with your parents. Yay! And we'll probably be taking final exams from home. So good luck.
Yeah. I think with that, we will wrap everything up. And I just wanted to thank everybody for being a great audience. And thank you, Susan, for giving us this first wonderful talk of hopefully a series of talks. I really enjoyed it, and I think everybody did too.
Well, thank you. Y'all take care.
Thank you.
Keep washing your
Everybody
hands. Yeah,
Yeah,
keep
stay
washing.
healthy.
Bye-bye.
Bye.